Good evening everyone and welcome to my YouTube channel. So here today we are going to be dealing with real gases. If you are new to this channel, kindly like, subscribe and share for more so that more content of this, you can view more content of this. So we are going to be looking at these three problems dealing with the real gas equation. So now what are some of the things that the real gases talk about? Now, under the ideal gas law, we made some assumptions to say the volume of a gas is negligible in comparison with its volume, which is true in a way. But at very high pressure, you will find that these gases tend to more like be packed together like that. So as a result, they occupy some significant volume. So that is what we mean by real gas equation. So the pressure is very high, causing the particles to be moving closer to each other. The other assumption is that under the ideal gas equation, we said that the temperature is very high, meaning to say the particles could be moving very, very fast like this. So this is the behavior portrayed under the real gas equation like that. They move very fast such that they do not have enough time to interact, that is to repel or attract each other. But at very, very low temperature, the gases tend to slow down like this. So now, as a result like that, they have enough time to interact with each other. So those are the two things that make the real gas to be possible. So number one, this occurs at very high pressure. So high pressure, you should know this for the exam. High pressure. Number two, we have high, low temperature. So we have a low temperature. So now so this is the real gas. So these are the conditions. For the ideal, it's the opposite: low pressure, high temperature. So now, the formula for the ideal gas is given as PV is equal to nRT. But for the real gas, we have something like this: P minus, we have our A, open brackets, the number of moles over the volume squared. Then we have our V minus, we have our number of moles times P should be equal to nRT like that. So nRT like that. So this is what we have. Sorry for that. So this is how the formula looks, plus. So P plus A, open brackets, number of moles over the volume squared, then we have that. So this is the real gas equation. Let's answer problems now. So these are some constants of A and B which you will be given in an exam. So these are the constants that you will be given in an exam like that. So now, when we do our calculation, let's begin with this one. So firstly, it says use the ideal gas equation and the van der Waals equation to calculate the pressure exerted by 1 mole of carbon dioxide in a volume of 0.05 liters at a pressure or at a temperature of 0 degrees Celsius. Explain why the two values are different. So we are going to have our PV. So according to the ideal, so using the ideal, we are going to have our PV is equal to nRT like that. Then we have our pressure will be over volume. So pressure is equal to nRT over the volume like that. So pressure should be equal to, then temperature must be in kelvins. So let's convert. Temperature in kelvins should be equal to temperature in degrees Celsius plus 273.15. We are going to add temperature in degrees kelvins should be equal to, we have 0 degrees Celsius plus 273. The value we are going to get is a 273.15 kelvins like that. Then what else do we have? We have the number of moles, 1 mole. We have temperature. We can just replace. So the number of moles is 1 mole. then we have times the, if we have the number of moles, 1 mole, the temperature is the volume is in liters, we can use the gas constant 0.08206 times the temperature, which is equivalent to, we have a 273.15. Then we divide this over the volume. So the volume that we have is equivalent to a 0.05 liters. So we are going to say 0.05 liters like that. Then when we do our subtraction, we are going to get a 0.08206 times 273.15. Then we divide by 0.05. We are going to find that our pressure is equal to 448.294, like that. So this is our value, atmospheres. So if you use these conditions, the units are atmospheres. Then to use the ideal gas equation, we are going to have our P plus our A, then N over V squared, like that. Then we multiply this by our volume minus number of moles times P should be equal to nRT. Let me explain a bit about this formula. Firstly, this number of moles, we know that the mole is the amount of substance. So if we have something, we have to account for how many substances are there. So then we have our B is just a correction factor, or the correction coefficient, because if a lot of gases are more like at one point like that, then it simply means to say this space, nothing can move through this space, it is rejected, in other words. So that's why we subtract the number of moles minus that. Then the pressure, that is the correction factor. Initially this is taken there like that. So then to make pressure the subject of a formula, we are going to divide over our V minus our NB, so that on both sides we have V minus NB. Now this form of the equation is very much simpler to remember in comparison with this form that we are going to show it. So if we cancel there, we are going to have pressure plus our A, then we have our N over V, then we have squared should be equal to NR T over, we have our V minus NB, like that. Then we are going to have our pressure should be equal to nRT over our V minus NB, minus, if this goes the other side, minus our A, open brackets, N over V squared, like that. So this is our pressure, like that. So if this is our pressure, what we are going to find now is, let's replace. So our pressure should be equal to, the conditions are the same. The number of moles, we have 1 times the ideal gas, 1 mole, like that. 1 mole times the ideal gas constant, which is, so should I say the gas constant, 0.08206 times the temperature was 273.15, then over our volume is equal to 0.05 liters. We are using the same, minus, we have 1 mole times the coefficient. Now which gas are we looking at? So we have use the Van der Waals ideal gas. So we are looking at carbon dioxide. So we are going to go on the constants for carbon dioxide and look for B first. So carbon dioxide, where is it? It's here. So look for B. B is equal to 0.0427, which are given 0.0427, like that. Then we subtract, minus our A value for carbon dioxide is equivalent to, we have a 3.59, like that. So we have a 3.59, we are going to go there, 3.59 more space. Then we have the number of moles, which is 1 mole over the volume is 0.05 liters, then we square this. So for this one, this is where how you use your calculator is very important. So 0.08206 times 273.15, this is going to give us a value of a 22.415 divided by, we have a 0.05 minus so 1 times this, so we have minus 0.0427. On there we are going to have a 7.3 times 10 to the power negative 3 minus, we have a 3.59. Then here the square of 1 divided by, so 1 divided by 0.05, we are going to get a 20 squared. This value squared, we are going to get 400. So what we have is 1 divided by this is 20, then we have the squared, then our pressure should be equal to, so we have our 22.415 divided by our 7.3 times 10 to the power negative 3. This gives us a value of 3070.55 minus what we have is, we have a 3.59, then 20 squared is 400, then we are going to have so subtracting this value, we are going to get 3070.55 minus 3.59 times 400. This is going to give us a value of 1634.55, like that. So this is the pressure for that one, which is in ATM. So this is the pressure of that one. So now here they have given us that the pressure, this one is correct, but for this one they made a mistake as one of the answers. The actual answer should be 1634.55 atmospheres. So now the question is, why are the two values different? So why the two values are different is due to the fact that for the ideal gas, number one, it ignores the volume of particles. Now this is very important, because already if we have, let's say, the volume like this, then we have particles of that size. That means to say these particles can only be able to move at all points except this space, like that. So there is always a volume that is excluded like that. So due to this factor, you might find that your pressure might increase, because pressure is the force per unit area, and if there is less volume, that means to say more pressure, like that. And for the ideal, it ignores pressure, and also for the ideal, it ignores the interactions which are the attractive and repulsive forces, though these forces tends to reduce the pressure because of the interactions and all that. So otherwise, that is how we go about that. So if we have this one, use the ideal gas equation and the van der Waals equation too. So the van der Waals equation is the real gas equation to calculate the pressure exerted by 1 mole of carbon dioxide in a volume of 0.2 at the temperature of this. Explain why the two values are different again. So the explanation there is the same. So what we are going to have, we know that it's pressure plus A N over V squared. This form is very much easier to more like remember for the exam. This is why we write it like this. Now when we made P the subject of the formula, we ended up with the pressure is equal to, we have nRT over our V minus NB. If you are good, you can remember from here, minus your A, then we have N over V squared. So then we are going to now replace, so it is still carbon dioxide, so we are going to say we have our number of moles, we have, is it 1 mole? So we have 1 mole times the universal gas constant. So we have 1 mole times the universal gas constant is 0.08206 times the temperature here 0 degrees, so everything is the same, so it's 273.15 like that. Then we divide this over the volume. Maybe the volume is different. We have a 0.2 liters minus our number of moles is 1 times our B was for carbon dioxide. The B value was equivalent to 0.0427 0.0427 like that. Then we have minus our A was 3.29 like that. Then we have a, is it 329 or is it, yeah, it's 0.59 not 29 but 59. So we are going to put 59 like that. Then the number of moles is 1 over the volume, which is a 0.2 for this one liters. Then we square this, so this value, then we are going to square it like that. So what we have is a 1. Okay, let's subtract there. So what we have is a 0.08206 times we have a 273.15. This is going to give us the same value, which is our 22.415. We divide this value divided by 0.2 minus 0.04427. Then we are going to get a 0.1573 like that. Then we have minus 3.59. Then 1 divided by that value is a 5. Then we have squared. Then we are going to divide 22.415 divided by 0.1573. This is going to give us a value of 142.498 minus our 5 squared is 25, so we have 25 times 3.559. This is going to give us a value of 89.75. So subtracting this, we are going to get 142.498 minus our 89.75. This is going to give us a value of 52.748 like that. So this is the pressure. Is it the same? So the pressure we have found is for the ideal, which is 52.7, which is which is the same. Then for the ideal, we were supposed to begin with the ideal. It's just PV is equal to nRT. So pressure is equal to nRT over the volume. So pressure is equal to the number of moles is 1 times 0.08206 times the temperature is equivalent to, we have 273.15. Then we divided by the volume, which is 0.2 liters, which will give us, so when we multiply our 1 times 0.08206, so when we divide that, we are going to get 112.1. So that is the pressure in atmospheres for the ideal, which was the first one here. So the reason is the same. So the difference is caused by the same thing. So at very high pressures, close to 1 atmosphere, due to the interactions, the pressure of the ideal gas tends to reduce like that. So that's why, not the ideal, the real gas, it tends to reduce due to the interactions, because pressure is built as a result of gases more like hitting the walls of the container. Now if there is more attraction, that means to say there will be less gases hitting the walls, therefore this reduces the pressure like that. So those are your reasons. So now let's look at our last problem. So what we have is calculate the pressure exerted by these moles in a 1 liter container at 25 using the ideal gas law. So PV is equal to our nRT like that. So this is the ideal. So P is equal to nRT over V. So our pressure should be equal to our N value is equivalent to, we have 1 more, or what do we have? We have 0.5 moles. So we are going to say 0.5 moles times the 0.08206 times the temperature. So temperature, you just get the temperature in degrees Kelvin should be equal to whatever you have, temperature in degrees Celsius plus 273.15. What we are going to have is 25 plus 273.15. This is going to give us a 298 like that, 0.15 kelvins. Then what we are going to put here is, let's move this a bit, temperature 298.15 kelvins. We divide this by our volume, which is the 1 liter there. So our pressure should be equal to, we have a 0.5 times 0.08206 times 298.15. This is going to give us a 12.2333 like that. So this is what we have for that problem. So this is our pressure in atmospheres. Then what we are going to have is for the ideal, remember, for the real, we have our P should be equal to, we have our nRT over our V minus our NB minus our A, N over V, then we have A squared. So our pressure here will be equal to, our number of moles is equal to 0.5 times this value is 0.08206 times 298.15. Then we divide over the volume, it's 1 liter minus our number of moles is 0.5 times B is 0.0562. Then this we are going to subtract minus our A value is equivalent to 6.49. So we have our 6.49 times our number of moles is equal to, the number of moles are equal to, we have 0.5 moles, 0.5 over the volume, which is our 1 liter. Then we square this. So we do our calculation. We are going to have 0.5 times 0.08206 times 298.15. We are going to get 12.23. We divide by, we have 1 minus 0.5 times 0.0562. This is going to give us a value of 0.09719 minus what we have is we have 0.5 squared. This is going to give us a value that is equivalent to, so we have 6.49 times 0.25 like that. So we have the 12.23 divided by 0.9719. This is going to give us a 12.5835 minus our 6.49 minus times our 0.25. This is going to give us a value of 1.625. When we subtract this, we are going to get minus our 12.5835. This is going to give us a value of 10.961 like that atmospheres. So this is our pressure. So that is how we go about those questions. Thank you very much for watching. Hope you would like, subscribe and share for more.